all measurements have error associated with them. No measurements are perfect. If you're doing a real scientific study, you handle that error with a statistical analysis. You find your standard deviation, your confidence interval. We don't want to do that much work. So we have a simple process called significant digits that we can use to help us with our handling the error of our measurements. There are two processes, two categories of measuring this error. Precision is how close repeat measurements are. So if you get onto the bathroom scale, on and off a few times, most likely bathroom scale reads down to the pound. And when you get on and off a few times, you might change by a few pounds. If you change by tens of pounds, then that's a poor bathroom scale. And the precision is usually built right into the measuring device. The precision is given to us by the number of significant digits that we get from the measuring device. But regardless of the precision, another thing is the accuracy, how close the true value is to, how close the measured value is to the true value. So if somebody messes with your bathroom scale, or you get on, you might look 10 pounds heavier than you were the day before. That's because they knocked the calibration off. So for some devices, the calibration is built into it at the factory, and we don't ever play with it after that. For other things, we have to calibrate on a regular basis. So when you're pumping gas, look at the gas pump. There's usually a circular sticker on it saying when it was last calibrated, because we don't want to get fights over how much gas we're getting when we buy gasoline. So the measuring device will give us its number of significant digits. And then from there, we have to figure out how to carry them through when we're doing multiplication, addition, subtraction. So let's take a look at a couple aspects of our significant digits here. So getting a number from a measuring device, we're going to treat the number as being significant except for placeholder zeros, so zeros that tell us where the decimal point are. So all the non-zero digits are significant. All the zeros that are between non-zero digits are significant also. Zeros on the left are not significant. That's because the only time that we have zeros on the left is to hold the decimal point for us. So zeros on the left are placeholder zeros. Zeros on the right, if we have a decimal point somewhere in the number, the zeros on the right are not placeholder zeros, so they are significant. If there's no decimal point in the number, then the zeros on the right are to show us where the decimal point is, and they are placeholder zeros. So placeholder zeros are not significant. All other numbers, all other digits are significant in that number. Exact numbers have an unlimited number of significant digits. So an exact number is a counted number. So a simple counted number, not an estimated number, but a simple counted number is exact. So when we're doing averages, we add up numbers, we divide by the number of numbers that we added up. That's the exact number that we're dividing by. Defined numbers, 12 inches is 1 foot. Those numbers are exact. So defined numbers are exact, counted numbers are exact. And then for using significant digits in calculations, we have different rules for different types of calculations. So we're going to start off with two calculations here. Addition and subtraction is one type of mathematical operation. And when we do addition and subtraction, we don't care how many significant digits that we have. We care where they are. So we're only allowed to keep the decimal place or column on the right of the number that is significant in all the numbers that we're adding and subtracting. So when we do addition and subtraction, we can actually increase the total number of significant digits or decrease the total number of significant digits. Because we don't care about the number of digits, but where they are, what column they're in. In multiplication and division, we care about how many significant digits that we have. So we're limited to the least number of significant digits in the numbers that we're multiplying and dividing. So this one's rather easy because we can just run it through our calculator, look at the numbers, find the least number of significant digits, and round our answer to that number. It gets more complicated when we're combining addition and subtraction with multiplication and division. I'll show a couple of examples of that. So when we decide how many digits our answer should have, then we have to round it to that. So we take the first column that we're going to cut off, that we can't keep in our answer. If it's less than 5, we just cut it off, making sure that we don't change the magnitude of the number. But if it's 5 or greater than 5, we're going to add 1 to the last number that we're keeping. So let's do some examples of this. Okay, so we get a number from a measuring device, then we have to figure out how many significant digits that we have. So this 0 on the left, we only put that there to help us find that decimal point, so we don't lose that decimal point. So that 0 is a placeholder 0. But since we have a decimal point on the left, that 0 on the right is not holding a decimal point for us, so it's not a significant digit. So we add up these numbers here, we have 5 significant digits. On the next number, the 2 zeros on the left are holding that decimal point for us. They're placeholder zeros. The one on the right is not holding a decimal point, so we're going to count that. So we're going to count up these numbers here, and we have 5 significant digits. On 2050, that 0 on the right is telling us where that decimal point is. Without us writing the decimal point there, we're going to assume that that 0 is placeholder 0 only and is not significant. So we're only going to count these 3 numbers. If you want to show that that 0 is significant, we can put a decimal point there, or we can write this in scientific notation. But in this case, we're going to assume that we have only 3 significant digits. 357.0, we don't need that 0 there to show us that decimal point. So the only reason that we put it there is to show that it is significant. So we have 4 significant digits. 1060.0, we don't need that 0 on the right to hold that decimal point. So it's not a placeholder 0, So that means it's significant. So we're going to count them all. So we have 5 significant digits. 153200. These zeros are showing us where the decimal point is. Without us putting that decimal point there, we're going to assume that they are not significant. So we only have 4 significant digits. And if we want to show that the first zero was significant and not the second one, the only possible way to do that is with scientific notation. On the last number, 2.010, we don't need to, this zero on the right is not showing us where the decimal point is, so it is significant. It's not a placeholder zero, so we're going to count all these. So we have 4 significant digits. Now, division is easy because we can just run it through our calculator and then look at the numbers to figure out the significant digits. So we got 3.60 times 10 to the third times 8.123 divided by 4.3 equals, and gives me 6800.65, and it continues on from there. I look at the numbers. We have 3 digits, we have 4 digits, we have 2 digits. I'm only allowed to keep 2 of these, so I can write this as 6800. That gives me the 2 digits, the 68. The 2 zeros are not significant. I need them there to hold the magnitude of the number, 6,800. So this is a good answer right there. On the next one, 11.5 times 8.78. I get 100.97. I have 3 digits, 3 digits. So we're going to cut it off right there. The first digit that we're cutting is greater than 5, so we're going to add 1 to the last that we're keeping. So this would just be 101. Next one, we have 2900 divided by 467. I got 6.20985. We look at the numbers, we have 3 digits. This 2900, we cannot consider that those zeros are significant. So we only have 2. So we're going to cut this down to a 6.2. The first digit we're cutting is 0, so we just cut it off. So 6.2. Then the other aspect, we have units. We're doing grams divided by mLs. They do not cancel off, so we're left with grams per ml for our units of the answer. And the last one here, we have 3 times 10 to the minus 4 times a 0.00199 equals, my calculator gives me 5.97 times 10 to the minus 7. We look at what we have. We have 2 digits, we have 3 digits, so we're allowed to keep 2. When we're keeping 2, we're going to be cutting off a 7, so we're going to round up, add 1 to that 9. So that will turn into a 6.0, our 2 digits, times 10 to the minus 7. And in scientific notation, we always only want to write the answer with significant digits only. We do not want to keep any non-significant digits in it. So in scientific notation, this number is always only significant digits. So let's do addition and subtraction. And here we have 0.0103 meters plus 2.56 centimeters. Now, in addition, in multiplication division, we multiply and divide the units. But in addition and subtraction, the units have to match first. So I'm going to convert this over to meters. So 1 meter is 100 centimeters. That moves our decimal point over by 2. So I'm seeing 2, 5, 6 would be meters. I go 1, 2, put the decimal point. We got 0.010. Let's see if this knows anything I'm doing. I didn't copy from there. Okay. 103. I had a different setup on this. Well, yes, okay. Meters, so we're going to add these up, 9530.0 meters. And there's nothing to cut off. We had the same number of decimal places on each one. We have 4 decimal places in both. We keep 4 decimal places in our answer. This one is similar in terms of we can't add dissimilar exponents. So I'm going to convert this lower one into a 10 to minus 3. So I want 10 to minus 3. I want to keep the top the same. So by going from 10 to minus 4 to 10 to minus 3, I made this number bigger. So 10 to minus 3 is bigger than 10 to minus 4. I made it by a factor of 1. So I'm going to move my decimal point 1 place here to make it smaller. 0.244 times 10 minus 3. Now I can subtract these. Let's do this in my calculator. And my calculator gives me a 6.876 times 10 to the minus 3. But on the same exponent of 10 minus 3, I have 2 decimal places, 3 decimal places. So I'm only allowed to keep 2 decimal places here. The first column I'm cutting is greater than 5. So I'm going to add 1 to that 7, round up. So I end up with a 6.88 times 10 to the minus 3. And the last one, I'll just run this through my calculator and then figure it out. 0.1654 plus 2.07 minus 2.114. My calculator gives me a 0.1214. I check. We have 4 decimal places, 2 decimal places, 3 decimal places. So I'm only allowed to keep 2 decimal places here. The first column I'm cutting is less than 5. So I just do a cut off 0.12, and that will be my answer there. So let's do a couple of the harder ones. Where we're combining addition, subtraction with multiplication, division. So I'm going to do this one with some pauses in my calculation, or I might have to backtrack at times. So I have 136.243 minus 79.52. Now I'll pause there. That gives me 56.723. Now keep going. Oh, wait. So I don't want to string. Oh well, let's do it. I didn't need that parenthesis. That doesn't sound right. Oh, might have written this down wrong, but I'll just keep doing what I have. So minus 25.1, and I really don't need that number at all. So I'll do the whole top of the calculation was 31.623. I'll just finish the calculation, divided by parenthesis 23.55 minus 7.2, close parenthesis, equals. So the whole calculation gives me a 1.934123, blah, blah. But I need to check this number down here. So we have 23.55 minus 7.2 equals 16.35. So between the addition, subtraction, and the multiplication and division, we have to check our intermediate answers to figure out what we're allowed to keep. So on the top, we have 3 decimal places, 2 decimal places, 2 decimal places. So we're allowed 2 decimal places. That gives us 4 significant digits in the calculation up here. On the bottom, we have 2 decimal places, 1 decimal place, so we're allowed 1 decimal place. So that gives us 3 significant digits. That's the least number of significant digits that we're allowed in our answer. The first number that we're cutting is a 4, so we get to keep a 1.93 for our answer. Over here, we're doing an average of 4 numbers. That means that that 4 is an exact number. It won't affect our significant digits. So let's try this out. So we add up 9.5 plus 4.1 plus 2.8 plus 3.175 equals, divided by 4 equals. And the number that we get is a 4. Oops, I went a little bit too fast on that. 4.8989375. And we go backwards. And this top number was a 19.575. So we need to check. We have 1 decimal place, 1 decimal place, 1 decimal place, 3 decimal places. We're allowed 1 decimal place. 1 decimal place gives us 3 significant digits. So we're allowed 3 significant digits in the answer. The first one that we're cutting is less than 5, so we're just going to cut it off, and we end up with a 4.89 for our answer. So we have 3 significant digits here, even though 3 of the numbers that we're averaging only had 2. And this is typical of averaging. That's why averaging our data improves the quality of the data. You can give us more significant digits by the time we're finished. And then one more here. So we do our 3.8621 times 1.5630. And let's see what that intermediate answer looks like. So we got a 6.03646623. Now complete it, minus 5.98 equals, that gives 0.05646623. So over here we have 5 digits. 5 digits. We're allowed 5 digits here. 1, 2, 3, 4, 5. So that gives us 4 decimal places. But we're subtracting 2 decimal places. So we're allowed 2 decimal places in our answer. So first number that we're cutting is greater than 5. So this will round up to a 0.06 for our answer. And so So when we do a addition subtraction, we can change the number of significant digits that were allowed. In this case, we've lost a lot of our significant digits that we're expecting after the multiplication.